All right, let's get right into it. We're going to pull back the curtain on one of the most important inventions ever, a kind of hidden force that's powering tons of devices we use every single day, the electric motor. You know the feeling, right? You flick a switch and something just starts spinning. It feels like magic, but it's not. It's pure science. So how in the world does electricity make something physically move? Well, that is the exact mystery we are solving today. Think about it. They're buzzing away inside remote control cars and all sorts of kids' toys. They're the reason your fan works, spinning those blades to cool you down on a super hot day. And get this, they're even vibrating like crazy inside your electric toothbrush. So to really get how all of these work, we've got to solve it like a mystery, piece by piece. Let's grab our first clue.
And clue number one, well, it all starts with the power source itself, electricity. Before we can make anything spin, we first have to understand how electricity even moves around.
So picture an electric circuit like a racetrack for electricity. It needs a totally complete, unbroken path to travel. It leaves the starting line, the battery, goes through the wires to power something, and then it has to make it all the way back home. If there's any break in that track, boom, everything just stops cold. Okay, now here's a really important detail about that flow. If you just flip the battery around, the electric current actually travels in the opposite direction. Now for something simple like a light bulb, it doesn't care which way the current's going. But for a motor, oh, this is the secret sauce. This ability to reverse the flow is everything. Seriously, lock that away. It's going to be a huge deal later. All right, let's put a pin in electricity for just a second and pick up our second clue. We're going to talk about another totally invisible force, magnetism. So, you've got your permanent magnets. They've always got a north pole and a south pole, and they are always on. The rule is super simple. You probably learned this in school. Opposites attract, and likes, well, they push each other away. Okay, so picture this. We put a magnet on an axle so it can spin around freely. If you bring another magnet up to it, snap, it'll line itself up, north pole to south pole. But here's the fun part. What if, at the exact moment they line up, you could magically flip the poles of that outside magnet? All of a sudden, the spinning magnet would be pushed away and pulled around to the new alignment. And if you could just keep doing that flip over and over, you could make it spin forever. And that idea, that endless rotation, that's the whole ballgame. Okay, time to connect the dots. We've got two big clues, right? We know we can reverse an electric current, and we know that flipping magnetic poles can make something spin. So, this is where it all clicks. What if we could use that electricity, the stuff we can reverse, to build a magnet that we can flip whenever we want? Well, it turns out you totally can. It's called an electromagnet. All you do is wrap a wire around a piece of metal, like a bolt or a nail, and run electricity through that wire. Presto, the nail becomes a magnet. But here's the really cool part. Turn off the power, and poof, the magnetism is gone. It's a magnet with an on-off switch. It's completely controllable.
And this is the genius move. Remember how we could flip the direction of the electricity just by flipping the battery? Well, guess what happens when you do that to our new electromagnet? You guessed it. You instantly flip its magnetic poles. North becomes south, south becomes north, just like that. We've just created a magnet that we can flip on command.
Okay, we have all the pieces to our puzzle now. We've got our flippable electromagnet. So let's put it inside the force field of some permanent magnets and see if we can make this thing spin for real. Okay, so follow the logic here. Step 1, we turn on our electromagnet. It immediately wants to spin and line up with the outside magnets, right? Opposites attract. But, and here's the key, the instant it gets there, we manually switch the wires. That reverses the current, which flips the poles of our electromagnet. So now you've got two like poles right next to each other, and they repel. They push it away hard. At the same time, the new opposite poles on the other side attract it, pulling it forward. And if you just keep repeating that flip, you get a motor that spins and spins. This is great. It works. But there's a huge problem, obviously. Who's going to sit there and flip the wires by hand 1,000 times a second? No way. We need a way to make this happen automatically. And the solution to that problem, well, it's just an incredibly clever bit of engineering. This is the final, crucial piece of the puzzle. This is what makes a motor actually work in the real world. It's called a commutator. And what it is basically a little copper ring with a split down the middle. This ring is attached to our spinning electromagnet. And then you have two little stationary contacts. We call them brushes that are always touching the ring. So as the whole thing spins, the brushes slide from one half of the ring across the gap to the other half. And every single time they cross that gap, they automatically reverse the flow of electricity to the electromagnet. It's just brilliant. This little setup does all the wire switching for us, automatically, with perfect timing, every single rotation. So as long as you've got power from the battery, that commutator makes sure the poles keep flipping at the exact right moment to keep that push-pull thing going, creating a nice, smooth, continuous spin. So there you have it. That's the basic idea. But, how do we get from this simple little spinning nail to a super powerful motor that can actually do some heavy lifting? Well, you basically just give it a few upgrades. Instead of just one loop of wire, you use thousands of loops or windings. Instead of just one electromagnet, you use a bunch of them, and they all fire off one after another to make the spin smoother and way more powerful. And, of course, you can just pump more electricity into it. All of these things work together to seriously boost the motor's rotational force, which has a proper name, torque. And hey, now that you get the basics, you can talk like an engineer. That stationary outside part, the permanent magnets in our example, that's called the stator. Stator for stationary, easy to remember. And the part that actually spins on the inside, with all the electromagnets, that's the rotor, or sometimes people call it the armature. So in the end, this whole beautiful dance between electricity and magnetism, it's all designed to do one simple thing: make something spin. And that simple rotational motion is what we harness to power, well, pretty much everything, from a tiny little drone to a gigantic industrial pump. So what we've just broken down is the basic principle of a simple DC motor. That's the kind you're going to find in all your battery-powered gadgets. But that leaves us with a really interesting question, doesn't it? Is this the same kind of motor that's powering a huge, incredibly powerful electric car? And if it's not, what's so different about that one?